Hello students, welcome to my YouTube channel Data Shah. In today's lecture, we'll be talking about the transportation problems. So that's another concept of operational research, where in this series we'll be talking about transportation problems and the assignment problems and its various methods. So what is a transportation problem? It's a special kind of linear programming problem, and in which the objective function is to transport the various quantities of a single commodity to the different destinations, so in such a way that the total transportation cost is minimized. So this is the problem for each business, and whether it's a clothing brand or whether it's a factory. So what is their task? Their objective function is to minimize their transportation cost. So they have their warehouses, and from the warehouses they have to just transport their goods to the commodities to the main destination. So they have to minimize that transportation cost. So this is what it looks like, that we have two sources here, as you could see. So one source can be go to the three destinations, and the three destinations have three different routes. So it is denoted by C11, C12 and C13. Similarly, the second source will also can go to the three different destinations with the three different routes. So we have this, and we have formulated this into the transportation problem. So what's our aim? Our aim is to find out the optimum transportation schedule, keeping in mind the cost of the transportation to be minimized. Second, the origin of the transportation problem is the location from which the shipments are dispatched, and destination is the location to which they have to be transported. The unit transportation cost is the cost that C11, C12 that you have just seen. It is the cost of transporting one unit of the consignment from the origin to a destination. So that's related to 1 unit. So this is what it looks like. We'll be formulating it in the table format, and above you can see here these are the destinations. So we have J destinations. Sources are I, so it's going from 1 to M. So here I is going from 1 to M. So these are the sources, and the destinations are going from J is going from 1 up till N. Now you could see here C11, C12 and the whole this is a sort of a matrix, you can say. These all are the unit cost of transporting one product. Now these AIs are the supply, so which is available to you, and below at the bottom you can see the these are the AIs, and sorry, the BJs are the demand and AIs are the supply. So this is how you will be getting a question, and we could see where M is the number of the sources, as I explained you. The number of destinations are N. AI is the supply at the source I. BJ is the demand at the destination J. CIJ is the cost per unit from source to the destination, and XIJ is the number of the units to be transported from the source I to the destination J. So it would be given in this format. So X11, X12, X13, X21, X22, X23. These are the number of units, right? And the cost is given to you, the CIJ, that is 15, 30. These are the costs. So this would be C11, C12, C13, C21, C22, C23. So these are the supplies. So here we are having the supply A1, A2, and this is B1, B2 and B3, the demand. We have three destinations and we have two sources, the same that I have taken the previous example. So there are again solutions that we'll be using in the transportation problems. So the feasible solution, the most important. What is a feasible solution? So in the linear programming problem, you might have heard about all these terminologies: basic feasible solution, the optimal feasible solution. So it is somewhat related only. Feasible solution is the non-negative values of Xij. So obviously we'll be taking the non-negative values only, because we are talking about the number of units. So they can't be negative. So always we'll be getting a feasible solution, and the non-negative values which satisfy the constraints of the supply and the demand is called feasible to the solution. So it must be a solution with the non-negative values. Basic feasible solution would be a feasible solution with M origin and N destination problem, where the number of the positive allocations is M plus N minus 1. So the basic feasible solution is again of two types, the degenerate and the non-degenerate basic feasible solution. So I'll be discussing it in the next slide. Now the optimal solution, feasible solution, is the feasible solution which will be which satisfies your optimality, that is minimize the total transportation cost, that is becomes your optimal feasible solution. So here in the transportation problems, we'll be calculating first of all the initial basic feasible solution, and then we'll be checking out using different method that what would be the optimal feasible solution. Is it equal to the initial basic feasible solution, or is it different? So let's consider every transportation problem. As I told you, it's a special kind of a linear programming problem. So obviously we can write it in the LPP format as well. So this is how we can write it. So the linear programming problem would be minimize this is our objective function. So it's minimization of the transportation cost. So it's minimize Z, summation I going from 1 to m, j going from 1 to n, Cij, Xij. So here we'll be writing it in this form: C11 X11, C12 X12 plus going on up till C1n X1n. So I had 3 only, so I'll be taking that example: C13 X13 plus C21 X21 plus C22 X22 plus C23 X23. So this is the example that I have taken, the 2 sources and 3 destinations. So this would be your objective function subject to the constraints. So as I was having to A1 and A2 only, so this would be equal to the Xij's, j going from 1 to n less than equals to Ai, and the demand we are having 3. So it would be Xij greater than or equal to B1, B2 and B3. So these would be our constraints, and the last one, the non-negativity constraint. Now if I write it in the standard form, then the standard form is always having an equality in the constraints, so I can rewrite it like this. So the objective function will not be changed, only the constraints would be in the equality format. So whenever you are asked that how you can write the transportation problem into the linear programming problem, so this is how we'll be writing it in the standard form. We'll be doing questions in the next lecture. So this is just the introduction part. In this now transportation problem is of 2 types, the balanced and the unbalanced. Now the balanced is when the total supply is equal to the total demand, then it becomes a balanced transportation problem. So summation Ai is equal to summation Bj. If they are unequal, then it becomes an unbalanced transportation problem. Now every balanced transportation problem has a feasible solution. So mostly we get balanced transportation problems only. If we get an unbalanced, we'll be having its own steps how we can solve that. So the total number of variables would be m into n. Such a solution consists of m plus n minus 1 allocations. So I told you, so m plus n minus 1, if you are having a basic feasible solution, then the number of the positive allocations would be equal to m plus n minus 1. So again, there are 2 types I told you, the degenerate basic feasible solution and the non-degenerate basic feasible solution. If the variables are less than, the positive allocation is less than m plus n minus 1, then it becomes a degenerate basic feasible solution. On the contrary, when it is equal to m plus n minus 1, that means we are having a non-degenerate basic feasible solution. So how we could solve the transportation problem? We have to first of all formulate our problem and set up it in the matrix format as I showed you. Now obtain the initial basic feasible solution. So we have various methods. We'll be talking about the 3 different methods, how we can find out the initial basic feasible solution. Then we have to test about the optimality, whether it is the optimal solution. That means, is it the minimum transportation cost that we'll be getting for our business. Then updating the solution. If it is not the same, how we could achieve that. We also be talking about the method for finding the optimal solution. So it has various applications. It is used to compute the transportation routes in such a way to minimize the transportation cost. It is used to find out the locations of the transportation corporation's depots where insignificant total cost difference may not matter. Minimize the shipping cost from the factories to the warehouses. Determine the lowest cost location for the new factory, warehouse, office, and the outlet. Find the minimum cost production schedule that satisfies the firm's demand and the production limitations. So whenever we are talking about the minimum transportation cost or minimum the labor hours or wherever we have the objective function of the minimized type, so we'll be talking about the transportation problems. So this was the introduction of the transportation problem, and in the next lecture we'll be talking about the methods of the transportation problem.